So we've just seen the fundamental theorem of calculus. And the fundamental theorem of calculus is essential for simplifying the process of computing definite integrals. But there's a key step: to find antiderivatives. And so hopefully now you see why it was so important that we began talking about antiderivatives and how to find them. And so there's a very naive way to think about antiderivatives, and that's reversing the derivative. So if I have some differentiation rule, I can just think about reversing that process of differentiating and then getting an antiderivative. And that works really well for certain types of functions. So for instance, power functions. We have seen that if I have something like x to the a and I want an antiderivative, well, all I do is add 1 to the exponent and divide by the new exponent. And this is of course true if a is not equal to negative 1. Okay, so we have this process of reversing the derivative for power functions. Same thing for trig functions. Or at least I should say for sine and cosine. At least right now, if I want to know an antiderivative of cosine of x, then because I know that sine is the derivative of cosine x, I know that this is just sine x plus c. Okay, so this works pretty well. But where's the problem? The problem comes in when the integrand, or the function that I'm trying to find an antiderivative of, gets more complicated. Okay, so for instance, what if I had the indefinite integral of natural log of x? Well, now all of a sudden I'm out of luck. Now recall, I know the derivative of the natural log function, but I don't know off the top of my head a function whose derivative is the natural log function. Okay, so it's not always so easy as reversing the derivative. However, it is possible to reverse some more of the differentiation rules. And so in this lecture, we're going to talk about the substitution rule. And now sometimes this is called sometimes it's called U substitution, but the substitution rule is what we will call it. And the way you should think about it is that it is reversing one of the differentiation rules. So it's reversing which differentiation rule? Well, it's reversing the chain rule. Okay, so recall, first of all, what the chain rule says. So the chain rule goes something like this. If I have that u is a function of x, like that, and then f is a function of u, or I can write that as y equals some function of u, well then the derivative of f with respect to x, so in other words dy dx, is equal to, well, f prime of u times g prime of x, like that. Okay, so that's what the chain rule says. So the idea behind the substitution rule is if I ever recognize inside an integrand something that looks like the derivative of something that's being composed with another function, then I should just be able to reverse or repack up the chain rule. Okay, so let me write down explicitly what I mean by the substitution rule, and you'll see the connection between it and the chain rule. Okay, so let's talk explicitly about what the substitution rule says. And as I said before, sometimes this is called U substitution. And the reason it's called U substitution is because typically when you do the substitution process, you use the letter U. Okay, so just letting you know some other common terminology for the substitution rule. U substitution. And now it's a technique of integration. Like I said, it's a technique to find an antiderivative, or by the fundamental theorem of calculus, to evaluate a definite integral. And so here's the idea. We're going to let U be g of x, which is differentiable, so just differentiable on whatever part of the domain we're interested in. And f of x is another function that is continuous. Now, where does it need to be continuous? It needs to be continuous on the range of g. And so the idea here is that we're actually going to compose f with g. So we want that f compose g to be continuous. And recall that because g is differentiable, it's continuous, and the composition of continuous functions will be continuous, so it'll make sense. Okay, so maybe just a side note that f compose g is continuous. Okay, so here's the idea. It's pretty simple. If I ever am looking for the antiderivative of f of g of x times g prime of x, well, this is just the derivative of f compose g. So what that means is that this is just the same thing as f of u du. Okay, and now notice what happened here. Remember that u is really equal to g of x. But now I'm actually changing the variable of integration. That's very important. So in the first integral, my independent variable is actually x. And in the second integral, my variable of integration is u. Okay, but I'm thinking about u as actually being a function of x. But you see that what is the advantage here? Well, this is complicated, right? So this might be, a complicated composition, and then you're multiplying by something else. So on paper, this looks complicated. But if I can sort of package up, so to speak, this g prime of x and this g of x in this way, noticing that what I'm composing f with, I'm also multiplying by the derivative of that same thing, I can actually just simplify the integrand and just say that this is f of u du. Just replace g of x with u and use u as the variable of integration. Okay. And like I said, as you can see, this is just f composed g, which is continuous, like we said. So it actually makes sense to take an antiderivative. And then over here, this really is the same thing as f composed with g, but I have this sort of factor of the derivative, right? So remember that this is really like du, okay? Because if u is g of x, then du as a differential is g prime of x dx, and then this really is just f of u. Okay, so I mean, the point is, the substitution rule is not really saying anything except that when you're integrating a function that looks like the function that's been differentiated by using the chain rule, it's the same thing as just integrating that function, kind of packing up the part of the chain rule you had. Okay, so it really is just reversing the chain rule. Okay, so I think it's best to sort of see some actual examples and to see the way the process works, because it's not always clear what to do and how to apply the substitution rule. So let's talk about the general strategy for using the substitution rule. Okay, so what is the strategy? And here I'm just going to call this use substitution, although what I'm really referring to is the substitution rule. So I have an integral. Let me give you an example of an integral where you can use the substitution rule. So let's say I have cosine of x squared times 2x. Okay, and I want to find an antiderivative to evaluate this indefinite integral. Okay, so what do I do? Well, the first step with use substitution is identify u. And like I said, u should be some function of x. And how do I know what to let u equal to? Well, the trick is you're trying to find a part of the integrand here that I can isolate, and that when I take the derivative of that thing I'm isolating, that function I'm isolating, the derivative appears as a factor of the integrand. Okay, so notice that in this case, I want to let u be x squared. Okay, and so why did I choose x squared? Since du dx is 2x, and 2x is a factor of the integrand. Okay, now it's not always easy to see what to do, but a lot of times that is exactly what you're trying to do. You're trying to identify a function or a part of the integrand where the derivative of that function also appears as a factor of the integrand. Okay, so then next, note that du is equal to g prime of x times dx. Okay? So all I'm saying there is that we're going to do a change of variables in the integral. So I'm trying to change to u. So I need to figure out what the differential du is in terms of dx. And then the final step is to substitute and evaluate. And when I say substitute here, I need to replace all of the x's in the integrand, as well as the variable of integration, this differential, with u's. Okay, so in this case, we have du is equal to 2x dx. And this is really nice because 2x dx is right here. I can replace that with du. And this is cosine of x squared, but that's really just cosine of u. So all in all, the integral cosine of x squared times 2x, I can just replace x squared with u and 2x dx with du. Okay, and now I've changed the variables, but now I can just take an antiderivative with respect to u. And that's pretty easy. This is just sine of u plus c. But then my final step, since I've taken the antiderivative with respect to u, I want to substitute back in what u is as a function of x. So this is really sine of x squared plus c. And that is the most general form of this function rate, of an antiderivative of this function. So I've evaluated the indefinite integral. Okay, so notice the key step is I want to take my original integral and replace everything with u. So I strategically pick u so that I can replace all of my x terms with u terms. And the hope is that that integral is easier to evaluate. Okay, so that's the idea. I'll mention that this strategy of u substitution can also, of course, be applied to definite integrals just by applying the fundamental theorem of calculus. But the real trick is, how do you find the antiderivatives? Well, when you recognize your integrand is a function that's the derivative of a composition of functions, you can just kind of reverse that process, reverse the chain rule, and get an antiderivative that way. That's all we're doing. Okay, so when you're applying the substitution rule, or use substitution for the first time, it can be really tricky, and I think that it's important to see several examples. So I'm going to go through, I think, 8 examples, some of indefinite integrals and some of definite integrals, and just show you the different things that you might be looking for to apply the substitution rule. And so the first thing to remember is that we're just looking for u. We just need to pick u correctly so that the integral or the antiderivative becomes easy to find. And so in this situation here, notice I have this factor of x cubed, and then I have 1 minus x to the 4th, all of that being raised to the 5th. Now, it seems like to me that this 1 minus x to the 4th is kind of a composition, so it's a function within the function x to the 5th. So that's a red flag to me to try u equals 1 minus x to the 4th. Right? So I'm kind of looking for an inner function of a composition. And the other thing that I notice is that when I take the derivative, or in other words, I find this differential, du, I'm going to get minus 4x cubed dx. Now, on first glance, that does not seem to be exactly what we want. What I notice is that I have an x cubed dx, and here I have an x cubed and a dx. So let me actually solve for x cubed dx. Well, I just need to divide by -4. So -1/4 du is equal to x cubed dx. And now I can actually substitute x cubed dx with negative 1/4 du. Okay, so let's see what happens when we substitute everything in. This integral, x cubed, 1 minus x to the 4th, all to the 5th, should be, well, 1 minus x to the 4th is u, so that's u to the 5th. And then x cubed dx I can replace with negative 1/4 du. And since negative 1/4 is just a constant multiple of the function u to the 5th, I can factor it out of the integral. And I'm really just looking for an antiderivative of u to the 5th du. But that I know how to do. So this is just negative 1/4. U to the 5th becomes 1/6 u to the 6th plus c. But now the last thing I want to do is actually replace u with what it is as a function of x. So this is negative 1 over 4 times 6 is 24. And then u is 1 minus x to the 4th. And then that's raised to the 6th power plus c. And the nice thing here is that you can verify. Just take the derivative of this function and you'll see that indeed the derivative does give me exactly the integrand I started with. Okay, so that's how a typical u substitution or substitution rule problem goes. Identify u, do the substitution. If you chose u correctly, or correctly enough, I guess, then everything will work out and you'll get a nice answer. Okay, so again, we see this function that we're trying to find an antiderivative of. And notice that it is the product of this function cosine x times this function cosine of sine x. And the goal is we want to choose an appropriate u that's going to allow us to simplify this integral by sort of reversing the chain rule. So here, notice that we're composing cosine with sine. And if I take the derivative of sine, I'm going to get cosine. So it seems like I should take u to be sine x. Okay, and then, like I said, du will be cosine x dx. And then what happens to the integral? Well, now we have the integral of cosine of sine of x. That's the same thing as cosine of u. And then look here. Du is cosine x dx. Here's cosine x, here's dx. So I can replace cosine x dx simply with du. And then we're almost done. So I just need an antiderivative of cosine u. But of course, an antiderivative of cosine u is just sine u. So this is just sine u plus c. But then if we plug back in what u is, which is sine x, we see that the antiderivative, or the indefinite integral, the most general antiderivative, is sine of sine x plus c. And that's how it goes. Okay, so this is a pretty simple example of a u substitution application, but it's important. It's important to practice this type of problem because it comes up a lot. And that's when you have a function where the argument is just a multiple of x. And so the key here is that we can just let u equal 3x. And when you get more comfortable with this, you actually don't need to go through this process. You sort of will see what happens every single time. But the point is that the differential just changes by this same factor of 3 that I'm multiplying x by. And so when I look at this integral, it's just going to be e, well, to the u. And now I only have a dx, but if I solve for dx, I see that dx can be replaced with 1/3 du by just dividing both sides of this equation by 3. So I have du, but the price is that I also have to multiply by this factor of 1/3. Okay, so this is pretty much always how it's going to go when you have a function where the argument is multiplied by a multiple, by a constant like 3. The antiderivative is just going to be divided by that constant. And so here we see 1/3 e to the u, because an antiderivative of e to the u is e to the u. And then we just replace u with 3x. And that's it. So again, it's very simple, but it's a very important application of u substitution that's good to keep in the back of your mind. So again, this can be a little tricky if you haven't seen an example like this before. But what I want to do is actually rewrite this integral in a slightly different form so we can really see what's happening. So this is the indefinite integral. So there's a factor of 1 over natural log of x. There's a factor of 1 over x, and then there's a dx. Okay, so that's really the same thing. I'm just isolating all of the different factors that appear in the integrand. So the key thing to observe here is this factor of 1 over x. And 1 over x is the derivative of natural log of x. Okay, so that's a red flag to tell me to set u to be natural log of x. And then du will be 1 over x dx. But now we have a direct substitution. Here's 1 over x dx. I can just replace that with u, and I can replace natural log of x with u. So here we have 1 over u du. So that's what this indefinite integral equals. And of course, this is natural log of absolute value of u. Remember, the absolute value is important, plus c. But then if I just substitute in what u is originally, up here, this is natural log of absolute value of natural log plus c. And that's it. Okay, so this one is also a little bit tricky. So you can look at it and say, well, I don't know an antiderivative right off the top of my head of this function. And it's not so easy to see exactly what to set u equal to either. So this is definitely a tricky problem, but it's something just to keep in the back of your mind. And what I want to observe is that I sort of have a factor of 1 over 1 plus. Now I don't have x squared, I actually have x squared squared. Okay, so 1 over 1 plus something squared, that sort of is starting to look like the derivative of inverse tangent. So here I'm just kind of doing some scratch work. I'm thinking about 1 over 1 plus x to the fourth is really 1 over 1 plus that quantity x squared all squared. And if I think about x squared, if I take the derivative of x squared, well then I'm going to pick up something that's sort of like x. Now it's going to be 2x, but that's close enough. So what that tells me to do is to set u to be x squared, so that du is 2x dx, or in other words, this x dx is just 1/2 du, so that the whole integral becomes x dx I replace with 1/2 du, and then the 1 over 1 plus x to the fourth is 1 over 1 plus u squared. Okay, so once you see it, it's like, oh, okay, I see now that this indefinite integral looks like inverse tangent plus c. But sometimes it takes a little bit of creative thinking to get it into a form of a function that you can think of an antiderivative. So this is just 1/2 inverse tangent of u plus c. But when we plug back in for u, we'll get 1/2 inverse tangent of x squared plus c. And that is that. Okay, so now we're going to look at some examples of definite integrals. And on definite integrals, the process to evaluate them using u substitution is exactly the same, except we just have the added step that we need to evaluate the antiderivative at the upper and lower limits of integration and take that difference. So here, this is another example of just a constant multiple to the argument. So I just let u equal 4t, and then du will be 4 times dt. Or in other words, I can just replace dt, if I divide by 4, by 1/4 du. Okay, so now an interesting thing comes up with the limits of integration, because the significant thing to notice is that these are t limits of integration. So when t is 0, I actually will need to replace my limits of integration with u limits. When I change my integrand and my variable of integration to u, I will also need to change the limits of integration. So when t is equal to 0, I just plug in 0 for t. I see that u is equal to 0. And now when t is equal to pi over 4, u is 4 times pi over 4, which is pi. So this integral becomes the integral now on u, so u equals 0 to u equals pi of sine of 4t, but that's u, and then dt becomes 1/4 du, so du, and then we pick up this factor of 1/4. Okay, so everything's the same. The only thing we need to remember to do is to actually change the limits of integration. And this is a really important step. Okay. Now I will mention that you don't have to change the limits of integration. You could just substitute back in to the original variable t, so just plug in 4t for u and you're done, and then you can use the t limits. I just prefer to also change the limits of integration. Okay, so the way this would go, the way I solve it, we have this factor of 1/4, and we need an antiderivative of sine u. Okay, but an antiderivative is just going to be minus cosine u, and then we just evaluate from 0 to pi. So this is negative 1/4 times cosine of pi is negative 1, and then minus cosine of 0 is 1. So negative 1/4 times 2, that's 1/2. And that's the area that we're looking for, 1/2. So we've evaluated this definite integral. Alrighty, so here we go. We have this definite integral that we're looking for, and the key step is being able to find an antiderivative of x times square root of x minus 1. And this seems a little tricky, and here we actually really just need to go with our gut. And our gut is that we're taking the square root of x minus 1. So that's like the square root of some function. So it seems natural, thinking about how the chain rule works, that we probably would want to let u equal x minus 1, because that is actually the function that is being composed. Okay? And then we see that du is actually just equal to 1 times dx, so there's a direct substitution. And then of course when u is equal to, when x is equal to 1, so the lower limit of integration, u is equal to 1 minus 1, which is 0. And then when x is 2, u is equal to 2 minus 1, which is 1. Okay, so let's start plugging everything in. So we're integrating. Now we're changing our limits to u. So the lower limit for u is 0 and the upper limit is 1. And then what about this x? All I know is that u is equal to x minus 1. But I can actually solve for x. If u is equal to x minus 1, that means that x is equal to u plus 1. So I can actually replace x with u plus 1. And then square root of x minus 1 becomes square root of u, and then dx just goes to du. That's a direct substitution. Now it's not obvious at first how to find an antiderivative here, but we're not too far away. So remember that square root of u is u to the 1/2. And I can actually distribute in u to the 1/2 and get the integral from 0 to 1 of u to the 1 plus 1/2, which is 3/2, plus u to the 1/2 du. And now I can take the antiderivatives of these power functions, the sum of two power functions. So this should be, I add 1 to the power and then divide by the new power, so 2/5, u to the 5/2 plus, this will be 2/3, u to the 3/2, all evaluated from 0 to 1. Well, when I plug in 1, I just get 2/5 plus 2/3, and when I plug in 0, I just get 0. So my answer is just 2/5 plus 2/3. But now 2/5, I can think about that as 6/15, and 2/3 is 10/15, so altogether the answer becomes 16 over 15. And that's the area bounded between the graph of this function and the x-axis between 1 and 2. Or in other words, that's the evaluation of this definite integral. Okay, so this integral here looks extremely complicated, but it's one of those situations where it's so complicated that it's actually easy. So what do I mean by that? I mean that all of this complicated stuff is set up so nicely to do a u substitution that it would almost be impossible to miss. Okay, so you see this sine inverse of x in this 1 over square root of 1 minus x squared. Well, if I can just recall that the derivative of sine inverse of x is square root of 1 minus x squared, then I'm basically there. So all I want to do is just let u be sine inverse of x, so that du is 1 over square root of 1 minus x squared, the derivative of sine inverse dx. Then let's think about the limits of integration. So when x is equal to 0, the lower limit, well, sine inverse of 0 is 0. So u is 0. And then when x is equal to 1/2, sine inverse of 1/2, well, I'm looking for an angle for which that angle, the sine of that angle is 1/2 between negative pi over 2 and pi over 2. That's going to be pi over 6. So u is equal to pi over 6. Okay, but now look what happens. This is awesome. So we have integral from u equals 0 to u equals pi over 6. And then sine inverse of x is u. And then dx times 1 over square root of 1 minus x squared is du. So everything gets absorbed back by reversing the chain rule. So this function was really just a function that came from taking the derivative of a composition of functions, okay? And so when we pack it all back up, it's really simple. So this is just u squared over 2 evaluated from 0 to pi over 6, okay? So pi over 6 squared is pi squared over 36, and then we divide by 2, that gives us pi squared over 72. And then when I plug in 0, of course that's 0. So I'm done. Pi squared over 72. So again, that's good advice. Sometimes the problems that look the most complicated look complicated because all the pieces are there to actually help you solve the problem. Sometimes these problems that are the hardest are actually the ones that look the simplest. But you see that it still is very important that you're very familiar with the common differentiation rules. It makes it a lot easier if you can remember, oh yeah, I have a sine inverse, I know what the derivative is. Oh, by the way, here's the derivative. Bam, done. Okay, one more just for fun. So here we have a rational function. We're looking for an antiderivative. So if we look hard here, let's see. It's not so obvious what to do. However, if we kind of go with our gut and look for a composition of functions, which I have that here, right? So if I look here, I have the function x cubed plus 12x that's being squared. So let me just try, and sometimes we really do just need to kind of guess and check until we get it right, but let me try letting u be x cubed plus 12x. Then du is 3x squared plus 12 dx. But notice this 3x squared plus 12. I can actually rewrite that. I can factor out a 3, and I'm left with x squared plus 4. But now x squared plus 4 dx is exactly what I have in the numerator of my integrand. And in fact, x squared plus 4 dx is equal to 1/3 du. Okay? And now let's think about the limits of integration. So the lower limit, when x is equal to 1, u is equal to 1 plus 12, which is 13. And the upper limit, when x is equal to 2, u is equal to 8 plus 12 times 2 is 24, so 8 plus 24 is 32. Okay, that looks good. Just double check. 2 cubed is 8, and then 12 times 2 is 24. 8 and 24 gives us 32. Okay, so putting this integral together gives us the following. So we put in our u, limits of integration, 13 to 32. Now what do we have for our integrand? We have 1 over this function squared, but that function is u. So we have 1 over u squared. And then we have du, so we replaced x squared plus 4dx with du, but we also need to multiply by 1/3. Okay, so we just need to find an antiderivative of 1 over u squared. But that's just negative 1 over u. So this will be negative 1/3 times 1 over u, negative coming from the antiderivative, evaluated from 13 to 32. But this is just negative 1/3 times 1 over 32 minus 1 over 13. And you can just leave it like that, that's correct. But if you do a little bit of subtraction of fractions, or maybe just use a calculator, either way, you can see that this is equal to 19 over 1,248. So that's the area underneath the graph of this function between x equals 1 and x equals 2. Or in other words, it's the evaluation of this definite integral.